In this example, we're given a circuit that has already been transformed to the phasor domain, and we're being asked to compute V0 using Thevenin equivalent circuits. Pretty much, we're being asked to compute the Thevenin equivalent circuit for this part of the circuit, and then connect the 10 ohm to it and to figure out what V0 is. And the way we find Thevenin equivalent circuit for circuits with sinusoidal sources in terms of AC steady state analysis is the same way we've done it for DC circuits, with the open circuit voltage and the short circuit current and so forth. So let me walk you through this here. So what I will do first is I'll take this circuit in here, and just this part of the circuit, we'll remove the 10 ohms to figure out what the V open circuit is, and then we'll replace it with a Y for I short circuit and so forth. All right, so here's the circuit. Let's start with the first part of it. Okay, so the first part in here tells me let's find the V Thevenin, which we can easily find. Maybe not easily, but we can find using, here's the V open circuit, okay? That's what we need to do. So how do we do this? Well, we're gonna have to use circuit analysis technique, and there's many of them. We can do source transformation, we can do nodal, mesh, whichever makes you comfortable. In my opinion, I'll use, or for this particular circuit, I'll use just nodal. So I'll call this here, for example, V1, and this one here will be V2, and V2 is V open circuit, by the way. I'll just call it V1 and V2. We'll solve it, figure out what V2 and V1 is, and we'll know our V Thevenin. Actually, the V2 is going to be the V Thevenin. All right, so let's do nodal at 1. So nodal at 1 tells me, well, -2 for the amps plus V1 divided by the 10 ohms plus V1 divided by the 5J. Plus we have V1 minus V2 divided by -10J. This is actually the current flowing through this one here. And of course, that leaves us with the current flowing through this dependent voltage source. And as you have seen, probably I've written it here. All right, there you go. So where's the V0? V0 happened to be here, which is the same as V open circuit, which is the same as V2. So I'll just utilize V2 for V0 in here. All right, so this current in here is actually flowing from here to here. So I need the voltage in here, which is V1, minus actually the voltage in here, but we also have this current or this source in here. If you rearrange them, you will see that what you're doing in here is 2V2 plus V2. That's what's happening in here. So you will be adding the V2 on top of that 2V2, and then you will divide them by the 10 ohms, and that equals 0. So this is what the equation should look like. So now we do a little bit of algebra to clean it up, and we will end up with the following, which is 2 minus J, and that's here is V1 minus 3 plus J, and that's V2, and should be equal 20. Okay, so let me highlight it, because this is the first equation out of 2 for the 2 unknowns that we have. And now we're going to do something very similar, which is writing the nodal analysis for the second node in here. So what we have is the following. We have first V2 divided by 5J, okay, plus we have V2 minus V1 divided by -10J. This is actually the current flowing here. And of course, we have the last current in here, which is the opposite to the one we just wrote, which basically is I believe it will be 2V2 minus V2, or plus V2, sorry, minus V1 divided by 10. This is pretty much the opposite of this one here. Okay, so what we need is V2, and of course we're going to add the 2V2 to it, minus the V1 divided by 10, and that should be equal to 0. So we do the algebra here to separate V1 and V2, and what we end up with is the following. -1, -J, V1 plus 3 minus J, V2 equals 0. So this is the second equation for the 2 unknowns. Now we write them in matrix format. That will be 2 minus J, -3, -J, -1, -J, 3 minus J, and that here is V1, V2, and that equals to, I believe, 20 and 0 in here. And using Python or MATLAB or any calculator, you should be able to come up with a solution. And that solution basically tells me that V1 is 6.67, 53.13 degrees in volts, and then V2 will be 2.98, and the angle is 116.56 degrees, and that's volts. And of course, V2 is the V naught is the V open circuit. If you remember, this is here is the V naught is V open circuit. It's not V naught the one that we're looking for. It's the V naught that we're looking for. We have to basically use Thevenin to find it, but it's V naught for this purpose of the circuit. Okay, so what we can do is we can just highlight this here and we say V open circuit. Let me just do that here. And this one here is V open circuit is just 2.98 and 116.56 degrees volts. This is the V open circuit. Let me just highlight it, and that's something that we're going to come back to when we're putting together the Thevenin equivalent circuit. So now that we have found the V open circuit, what we need to do right now is to find the R Thevenin. So there are different methods to find R Thevenin. If we only have independent sources, we can basically turn them off and figure out the R Thevenin or the R equivalent from that point. But unfortunately, this does not apply in here, and the reason why is because we have this dependent source. So the only solution for us is the second method or the third method, which is basically either find the I short circuit or connecting as a source and turning off this source in here and figure out the voltage or the current depending on what type of source. I will utilize the method that basically tells me, okay, let's remove this here. And what we will do is we will connect it with the wire in here, and we'll figure out what this I short circuit in here is. And based on that I short circuit, we just basically utilize the V open circuit, I short circuit to figure out what R Thevenin is. All right, so how can we find this short circuit current? Well, multiple ways. Again, it's up to you. The one I will be utilizing is nodal, and the reason why is we only have to write one equation. So let me tell you why it's one equation. Because this node here is basically the same as here. So this one here now is the same node. So I don't need to write a nodal for this. Of course, this one here from here to here is actually the V naught for this particular circuit for this one here. And of course, V naught is 0. So this is also here, if you think about it, this is also a 0. So technically, I can just turn this source off. Again, this is just because of this situation now. So because this is a 0 here. And now we can write nodal analysis equation to figure out what this V1 is. And based on that, we can figure out what the I short circuit is. All right, so let's write nodal. So nodal at V1. So what we'll get is -2 plus V1 divided by 10 plus V1 divided by 5J plus V1 divided by -10J. This is actually this current in here, and this is 0, V1 minus 0, okay? Plus, I believe it will be V1 divided by 10 ohm equals 0. And that tells me that V1 is, the answer is 8.94. And the angle is 26.57 degrees, and that's actually in volts. All right, so we found out what V1 is. Now, multiple ways to find what the I short circuit is. But frankly speaking, we can just basically say, well, it's the current here plus the current here plus the current in here. Okay, and of course this current should probably be 0 because the voltage across here is 0, so this is technically shorted out. So all we have to do is just figure out this current, and it will be equal to the I short circuit in here. All right, let's do that. I'll write KCL at this particular node in here, okay? And this KCL will tell me it's V1 divided by -10J plus V1 divided by 10. That basically is this current plus this current should be equal to I short circuit that I'm looking for. But we already know what V1 is, so that tells me what I short circuit is. And that happened to be 1.26, and the angle is 71.57 degrees. And that here is in amps because everything is in ohms. All right, so we know what the I short circuit now is, or actually this is also I Norton if you want to use the Norton equivalent. But anyway, this is it. So we have everything we need to actually compute what we're looking for. So let me just move this here so that I don't have to scroll up and down. Okay, so we'll do this here. So we have the I short circuit and the V open circuit. So the R Thevenin, well, this time it's not called R Thevenin, it's Z Thevenin because it's impedance. It's actually V open circuit divided by I short circuit. So you take these two numbers and you divide them by each other and you get 1.67 plus 1.26 1.67J ohms. So we typically write the Z in rectangular form because this tells me this is a resistance and this is an inductor, and I can replace it that way if I wanted to. All right, so what's the Thevenin equivalent for the whole circuit? Well, the Thevenin equivalent is the following: plus minus, it's 2.98, that's the voltage source, and the angle is 116.56 degrees. Okay, and what do we connect it to? We connect it to this impedance, the one that we just found. Okay, so this impedance is here. I can either draw it as a box that has this particular impedance, or I can draw it like, well, it's a resistor and an inductor. So this is 1.67 and this is 1.67J. Either way is fine. Okay, and then what do we connect it to? Well, we connect it to the original resistor here. This original resistor that we have was 10 ohm, and we're looking for the V0 around it or across it. Okay, so what we need to do is connect this one here and figure out the plus minus V0, and I believe this is 10 ohms. Okay, so how do we find this? Well, simple. V0 is just using voltage division 2.98. Okay, and the angle is 116.56 degrees times 10 ohms divided by 10 ohms plus 1.67 plus 1.67J, and this answer will be 2.53, and the angle is 108.42 degrees, 42 degrees, and this is in volts, and this is basically V0. This is the answer we've been looking for.